So we can start. So welcome everyone to this week's talk in the virtual seminar on geometry with symmetries. So it's a pleasure to welcome Jesús Núñez Zimbrón from UNAM, the National University of Mexico, who will talk about cohomogeneity on RCD spaces. Welcome. Thank you. I'm sorry, but for some reason I cannot hear you. Can you hear me? Can everyone else hear Jesus, or is it only me?
Yeah, I can hear you, Fernando, but not from Jesus.
Not Jesus. Okay, thanks. Thanks, Bofan.
Can you hear me now?
Jesus, maybe
Okay, yeah, now, yeah.
it's
Okay.
working. Yes, perfect.
And,
So,
okay. Wow, so I've
okay,
been some technical difficulties. Yeah.
perfect.
Okay.
Thanks.
Yeah. So you can hear me okay now.
Yes.
All
Thanks.
right, thanks. Yeah, so I was just saying thanks to the organizers for the kind invitation, and thanks, Fernando. And so I'm going to speak about a joint project with Diego Corro from Cardiff and Jaime Santos from Madrid. Who I think is in the audience. Jaime is in the audience, so if I'm unable to answer something, I'm sure he will be able to answer it properly. And yeah, so the plan for my talk is I'm gonna give a little bit of a recap on cohomogeneity one manifolds. Like for the whole talk, I'm gonna try to be not so technical. I'm not gonna worry about like the technical aspects of the results. So if I'm a little bit sloppy with some hypotheses, I apologize to the experts. I'll try to just focus on the main ideas. And then I'm gonna speak about like one of the key points of our project, which is like a slice theorem for metric measure spaces, for cohomogeneity one metric measure spaces, which in fact works with without curvature assumptions. So that's one of the main points. And then I'm gonna recall a little bit about RCD spaces. So I apologize if there's like to Professor Wave probably knows this like inside out. So I apologize for a little bit of basic stuff. And then I'm gonna focus on another main key point of our work, which is sort of how to give a curvature bound to the, like, combine the slice theorem with the curvature bound, say. And then finally, I'm gonna mention how to apply this to low-dimensional RCD spaces, right? So as I said, I'll try not to be too technical, so I apologize for that. Okay, so just to settle the notation, right? I'm gonna denote the orbits of points like this. So if I have a Lie group G, right, and a manifold say M and a point X, I'm gonna denote the orbit like this, and the isotropy subgroups like this, right, which are closed subgroups of G. And there's a usual identification of the orbit, right? So you can identify the orbit as a quotient of G mod the isotropy of X at each point, right? I'm usually gonna consider compact Lie groups and effective actions usually. So I'll try not to, I'll probably be sloppy with this as well. So I apologize for this. And I want to recall three main tools that one uses in the theory of transformation groups that are sort of like the core tools that one needs to identify manifolds on which some group acts. So the first one is the Myers-Steenrod theorem, which says that the isometry group of a Riemannian manifold on which, the isometry group of a Riemannian manifold is a Lie group, right? And it is compact if the manifold itself is compact, right? So this is one of the main tools. And the second main tool is the so-called principal orbit theorem, right? Which says that if I look at the set of points on the manifold, which are on orbits of maximal dimension, then this set is open and dense in the manifold, right? So this gives me sort of like a big set where I can identify my manifold. And probably like the most crucial tool in the theory of transformation groups is the Slice Theorem, which Kosul proved, which says the following. I'm actually gonna go ahead and pass to the next slide. So it says the following. So if I have a compact Lie group acting by isometries on M, so this is a subgroup of the isometry group, then I can always find a sufficiently small epsilon so that a small tubular neighborhood of the orbit of radius epsilon, this is equivalently homomorphic to a so-called fiber product like this, right? And so the idea being that I'm gonna tell you what S is in a few seconds, right? But the idea is that here's the orbit. Here's the orbit. This is my point. Here's the orbit, right? And then if I grab a small enough tubular neighborhood like this, then I can separate sort of like in the transversal directions to the orbit and the directions along the orbit, right? So I have this so-called slice, right? And the isotropy of my point acts on this slice, right? So I can sort of separate the action into parts, like what happens along the transversal direction to the orbit and what happens like along the orbit, right? And just to like properly define what a slice is in the most general case, so a slice is the following, right? A slice at a point X is a set, right? Which contains X and which is closed in the saturation of the slice, right? Also, when you take the saturation of this set, it is an open neighborhood of the orbit, right? Then it is invariant with respect to the isotropy. And if it happens that you move the slice, right, or your candidate to be a slice, if you move it, right, and then it still intersects the slice, then it means that this G, it was in the isotropy of X, right? So this is sort of like the most general definition of a slice. Of course, in manifolds, you can define it using like the tangent space in a more comfortable way, but this is gonna be better for our purposes. So now there's when you go to cohomogeneity one manifolds, what this means is that you look at the quotient space of the action, right? And then you impose that the dimension of the quotient space is one, right? This is usually called the cohomogeneity, right? The dimension of the orbit space. So for cohomogeneity one manifolds, there's like a deep structure theorem. One can give a very nice structure theorem for these manifolds. And one of the crucial tools to do this is the so-called isotropy lemma from Kleiner, right? Which let me maybe do a little bit of a drawing here. So maybe I have like the sphere S2, right? And then I act by rotation, say S1 acts by rotations, then the orbit space looks like an interval like this, right? And I can take this interval and lift it to a geodesic on the sphere, right? So it looks sort of like this. I can take like a section of this action, right? And then this geodesic, what it happens here is that if I look at the isotropy on all of these points, these are all conjugated to one another, right? And all of these in the interior of the geodesic are subgroups of the isotropy in endpoints, right? And this is like a general fact for cohomogeneity one, or in fact for actions, right? And then one can use, like I was saying, this is a drawing, right? Then one can use these Kleiner's lemma to give like a structure theorem for cohomogeneity one manifolds. So first of all, because of the dimension, the quotient, it has to be homomorphic, at least one of these options, right? Since it's one-dimensional, the quotient space has to be, say, a circle or an interval. We can say -1 to 1, right? Or a semi-open interval, like a ray, say, or the full real numbers, right? And then we have different situations for each of these possibilities, right? What I put here is like the usual structure theorem for cohomogeneity one manifolds. Maybe I won't go along for like too detailed for this, but like for each of these options, one gets a structure, a topological structure theorem for the space, right? What maybe is sort of important here is how one obtains this structure theorem. So coming back to the sphere example, what one does is sort of like to choose a principal orbit here, so like a middle orbit here, right? And these functions like a separation point, right? Like from here to here, one can see like a cone bundle, say, right? Like it's made up of like a fiber bundle, and from here to here, something similar happens, right? This is what happens, for example, here. Right. I'm going a little bit fast. I'm assuming like this is sort of well known, but if this is not so clear, please let me know. Okay, so this is what we sort of like the starting point that we began with. So our question was, is it possible to talk about or do something like this for metric measure spaces, say, like with some type of curvature bound, right? And now, yeah, sorry, I forgot about this. Let me also say what this. There's another bit of information here. In the specific case that the quotient space is an interval, right? We have a group diagram associated. Because if we look at the isotropy, like in the interior of the quotient space, this is going to be constant up to conjugation. Say we call it H, right? And then this is going to be a subgroup of the, say, lateral isotropies, right? Let's call them K minus and K plus, right? And all of these are subgroups of the full group H, G, that's acting, right? So we have like a group diagram that comes with the cohomogeneity one manifold in this case, right? And we have like a little bit of more information because if you look at these lateral isotropies and look at the slices, right? If we have one of these slices, these lateral slices, then these isotropies act transitively on the boundary of the slice, right? And so what this means is that these quotients, right, these K minus and K plus mod H, these occur as homogeneous spaces, right? And so we have a little bit of more information here. Right? And so for each cohomogeneity one manifold with this interval as a quotient space, one can assign this group diagram. And conversely, given a group diagram with this condition, one can construct a cohomogeneity one manifold, right? Okay, so what happens for metric measure spaces? So we wanted to ask this question in a more general setting, like possibly with some curvature bound notion. And like the first thing maybe to mention is that the slices like itself, like the sets themselves, like the existence of these sets is very well like known, even from like the 60s from Palais. So the theorem of Palais says that every completely regular space, it has a slice at every point, right? So say like the existence of these sets is very well known. We don't have to worry about this, right? But when we add more structure, right? When we are, for example, like a curvature bound, then we can usually say more about the slices, right? For example, in the Alexandrov case or in the smooth case, which in the Alexandrov case it's due to Harvey and Searle in 2017. What happens is that the slice acquires more structure, right? It becomes a cone over a positively curved Alexandrov space. So when putting more structure to the space, it's possible that we acquire more structure on the slice, right? And so even though we already have the existence, it's interesting to ask if we can do this, for example, for RCD spaces as well, if the slice acquires some RCD structure, right? Like the bad news here is that all the known proofs of the Slice theorem, even in the Alexandrov case, they require a notion of like a space of directions, right? Like a tangent space and some form of the exponential map or some notion of like a infinitesimal to local relation, sort of in the spirit of say like the normal neighborhood theorem in manifolds or like the conical neighborhood theorem of Perelman, right? And this is like completely missing in the RCD setting as of now. Even though there's a notion of space of directions, but it only functions almost everywhere. This is a paper of Han and Mondino, if I remember correctly. And there's definitely no good notion of exponential map or there's definitely no good understanding of like an infinitesimal to local relation in these spaces, right? So basically what this means is that we have to find a proof that it's not like this, right? Like that it's not like sort of Eulerian, that it's more like Lagrangian in nature. Like these proofs tend to work better in RCD spaces, right? And so this is what we set out to try to find. And so actually for this first part, as I mentioned, this works without any curvature notion, any curvature bound notion. So I'm gonna talk about metric measure spaces like in abstract for a while. So let me take, right, metric measure spaces where the space is, the metric space is complete and separable. And the measure is a Radon measure, which gives finite mass to bounded sets. This is enough to make everything work, right? I'm not gonna be too careful with the hypothesis, but this should be enough for everything we say. And so let me remind you a little bit about some notation. So first of all, let me denote like this, the space of Borel probability measures on X, right? And a subset of this, let me call it P2. This will be the space of probability measures which have in addition finite second moments, right? Which means that these integrals are finite. And for these measures, we can define a distance, which is called the Wasserstein distance, right? So the Wasserstein distance, or the two Wasserstein distance between two measures, mu0 and mu1, is the infimum of these type of integrals, right? Where this d is the distance in my space. And these rows, these are so-called couplings of mu0 and mu1. What this means is that these are probability measures in the product of x times x, and their marginals are mu0 and mu1, right? So when you push forward to each of the factors, you get mu0 and mu1. And one can prove actually that there are always measures realizing this distance, right? Which are called optimal transport. This definition, this notation comes from the theory of optimal transport. And well, I'm not gonna dwell too far into that, but just to call them the proper name. Right? And okay, and there are some like a couple of known facts which are important for this. And so one of these facts is the following, right? So first of all, if my space is geodesic, then this Wasserstein space, I'm gonna call it, right? So the space of measures with finite second moment equipped with the Wasserstein distance. This Wasserstein space is also geodesic, right? And there's an equivalence. These are characterization of geodesics. So a curve of measure is a geodesic if and only if there's a measure, sorry, on the space of geodesics of X, which I denote like this, right? Such that when I push forward with the evaluation map, so this ET, this goes from the space of geodesics to X, and what it does is that if you give him a geodesic, then it just evaluates it, right? So when you push forward with this evaluation map on the endpoint, then this gives you an optimal transport between the endpoints, right? And at each time, the geodesic looks like just pushing forward this eta with the evaluation map, right? So we have a nice characterization of geodesics in the Wasserstein space. I'm gonna denote the set of all of these type of measures like this, right? So optimal geodesic. And so one thing that we will require for our spaces is that geodesics behave somewhat nicely. I'm gonna require that the space is so-called essentially non-branching. Let me remind you what this means, right? So I'm gonna say that my space is essentially non-branching if for every pair of probability measures in P2, which are absolutely continuous with respect to this reference measure, and every optimal, every geodesic, say, between them, right? This is concentrated on a set of non-branching geodesics, right? So the geodesics on which this measure is concentrated cannot do this, right? This, I hope it's not it doesn't look like an artificial hypothesis, right? And there are many classes of spaces that satisfy these. So manifolds certainly satisfy these. And Alexandrov spaces are not only essentially non-branching, but even non-branching, right? Like every geodesic is non-branching. And also RCD spaces are essentially, in fact, non-branching, right? So this is like a fair hypothesis, I think, right? Okay, so one of our main results is this, right? So if we have a space which is essentially non-branching, on which a compactly group acts by isometries, say, right? And the quotient space, which I denote like this, is isometric to one of these options. So basically, I'm requiring that it is of cohomogeneity 1 in some sense, right? Then we have a characterization of slices, right? We know by Palais that slices exist, but we can give a specific characterization of slices in the following way. So for every point, there exists some radius, delta 0, positive radius, such that for any smaller radius, delta, we have that the following set is a slice. So my set is this. So it's the set of all points, right? Such that the distance from y to x0 equals the distance from y to the orbit at x0, right? And then intersect this with some ball of radius delta, right? So basically, I'm looking at points such that the distance to this x0 is the same as the orbit, right? So I wanted to say something about the proof, like some rough sketch about the proof. And actually, the proof relies on proving that horizontal geodesics, what we call horizontal geodesics, cannot branch. So let me tell you about this, right? So I will call a geodesic gamma horizontal if when you project it to the orbit space, so this is going to be the quotient map. When you project it to the orbit space, this is also a geodesic in the orbit space, right? And so I want to prove that horizontal geodesics are the ones that, like when you project it, say, when you project these geodesics, you don't lose length, right? So first, let me tell you that horizontal geodesics are precisely the geodesics that realize the distance between the orbits at the endpoints, right? So say you have some geodesic such that when you look at the distance from the endpoints, right, this is the same as the distance in the quotient space. So this is like the usual orbital distance, right? This is the same as the distance between the orbits, right? And I want to see that this geodesic is in fact horizontal. So take any two parameters, S and T, say S smaller than T, and I want to show that this, like the geodesic is horizontal for these two parameters, right? So first of all, like when you evaluate a test, there's always some G. You can always translate using the action so that this is true, right? You can always realize the distance between the orbits at time S and time T by translating by some G with the action, right? But then like using like a couple of triangle inequalities very easily, we see the following, right? So the distance between the orbits at 0 and at 1, using the triangle inequality, you can decompose it like this. This is less than or equal than this, right? But then this is less than or equal than this because this distance, right, is supposed to realize the distance between the orbits. So we have the inequality here, right? And this here is actually equal to this here because G is an isometry, right? And so putting these terms back together, we get the distance from gamma 0 to gamma 1, right? And we assume that this distance was exactly the distance between the orbits, right? So we sandwich everything, and so we have this conclusion, right? So so the geodesic is horizontal for every S and T, say, right? Okay, so we can look now at what happens at the level of the Wasserstein space with this situation. So let's graph two measures. Let's graph, say, mu g and nu g, two probability measures on X, which are G invariant, right? What I mean by this is that when you push it forward, which is with each G in G, then the measure remains the same, right? And now what I claim here is that any geodesic, any Wasserstein geodesic between these two measures has to be supported on horizontal geodesics, right? And actually, I use here, we use here some results from Fernando and Martin Kell and Andrea Mondino and Gerardo Sosa from 2018, where they prove that when you have an optimal transport between G invariant measures, when you push it forward to the quotient space, then you also have an optimal transport, right? And so we have this. But then we can use this fact to do the following computation, right? So the Wasserstein distance upstairs, it coincides with the Wasserstein distance downstairs, right? With respect to the push forward of the optimal transport. And then just by definition, this integral is this, right? But then this means that this integral is 0, right? But now the distance downstairs, because pi is a submetry, is always less than or equal to the distance upstairs. So this integrand is always non-negative, right? And so this means that all of these term has to be 0 almost everywhere, right? So basically what we're saying here is that for each pair of points on the support of this optimal transport rod that we took upstairs, it has to be, these points have to be joined by horizontal geodesics, right? And so this is what happens at the level of the Wasserstein space. And now we can use this fact to see that actually horizontal geodesics cannot branch. So let's assume by contradiction that they do branch, right? So we have two branching geodesics, right? Say gamma 1 and gamma 2. And now one observation is that when we move it with the action, when we move these two geodesics with the action, they also branch, right? So if we have a couple of branching geodesics, then we have like many branching geodesics, right? And so, okay, so this is the first observation. Now, let's look at what happens on the quotient space, right? So for the endpoints of these two geodesics, say, let's look at the first geodesic, gamma 1, and look downstairs at what happens with the orbits, right? So for simplicity, assume that these two orbits are joined by a unique geodesic in the orbit space, right? For general geodesics, this might not be true, right? But then we can assume this situation, right? And so if they are joined by a unique geodesic, then when we project with the quotient map, then it must happen that for all times, the projection of the first geodesic coincides with the projection of the second geodesic, right? Like even though these branch in the upstairs, then when we project them, they go to the same geodesic, right? And now we're gonna use this fact to produce many branching geodesics and some measures which are not supported. Sorry, an optimal transport which is not supported on non-branching geodesics, right? So let us take the following probability measures, right? I'm gonna take the push forward measure from the space to the quotient space, but restricted to the image of my first geodesic up to the branching point, right? And normalized, so it's a probability measure. And similarly, I'm gonna take my push forward measure restricted to the image of the first geodesic, but after the branching point, right? And normalized so that it is in fact a probability measure, right? And now I'm gonna quote again the work from Fernando and company here, which says that if I have these two measures in the quotient space, then we can always get a lift upstairs, right? We can always construct unique invariant measures, say mu1 and sorry, mu0 and mu1, which are absolutely continuous with respect to the reference measure, which are lifts of these two measures that I graphed, right? And now what we saw before is that any optimal transport between G-invariant measures have to be concentrated on horizontal geodesics, right? So if I take optimal transport between these measures that I got from Fernando's work, then they have to be concentrated on horizontal geodesics. Let's call these sets of horizontal geodesics gamma 1 and gamma 2, right? And but now here's like the catch. I can get a different optimal transport here, right? If I average the optimal transports that I had, then whoops, sorry about that. If I average the optimal transports here, then I get a new optimal transport, right? You can see directly that this is still an optimal transport. But then this optimal transport is concentrated on the union of the sets of geodesics on which row 1 and row 2 were concentrated, right? And this is branching. This union of geodesics is branching everywhere, right? So this contradicts the previous fact that we saw that any optimal transport on for G-invariant measures have to be concentrated on non-branching geodesics, right? Okay, so so far so good. Is everything okay so far? Yeah, okay. Yeah. So like up to here we have two nice consequences because what we have here is that we saw that for horizontal geodesics they do not branch. And so actually we can recover like these two principal tools from the classic theory of transformation groups, right? The usual proof of Kleiner's lemma is it rests on the fact that these geodesics that cross transversally every orbit, that they do not branch, right? And so the usual proof of Kleiner's lemma works now that we have here this fact for horizontal geodesics, right? I'm not gonna give the proof here, but it's quite easy to produce, right? Also this so-called principal isotropy lemma. So the fact that all the isotropic groups in the interior of the quotient space, all those are conjugated to one another, right? So up to conjugation, they are the same group, right? Okay, so now we have basically all the elements that we needed for like to reproduce the same theorem from the classical manifold structure theorem for cohomogeneity one manifolds, right? And just to say a bit of the actual proof that this is a slice, right? I'm just gonna say one of the key points of the proof because it's lengthy and it's not so interesting now that we have this, right? But just to say like one line about this. So we would want to prove that this set that I had, right? Let me backtrack a little bit. So we have to prove that this set, so the set of points on horizontal geodesics, say, stemming from x0, we want to prove that this is in fact a slice, right? So I can go through the definition of the slice and check each of the items manually. Like I have to prove that this is in fact a closed set on the saturation of the slice and so on and so on, right? I'm just gonna prove one of these items, say like as a proof of concept, right? So say I have some G in my group, right? So that when I move the slice by G, it intersects the slice still, right? I'm gonna try to prove that this G is in fact on the isotropy of x0. So first of all, just observe that when you move G, when you move the slice by G, this is in fact just to take the slice at G times x0, right? And now if I have a point on the intersection of this slice at gx0 and the original slice, then what we're saying is that the distance from y to gx0 is the same from y to x0, right? But this was in fact equal to the distance from y to the orbit of g0, of x0, right? And now, so what we wanted to say here is that, in fact, this forces gx0 to be the same as x0, right? If this was not the case, right? If there was like a different point, say if I have x0 here, and say that I have gx0 here, and there's some y here, right? If it happened that this gx0 and it was different from x0, then we would have a branching geodesic here, right? Horizontal branching geodesic, and this we saw that this is not possible. So in fact, what has to happen is that gx0 is equal to x0, right? But then this means that g is a part of the isotropy of x0, and so sort of this is like one of the like a standard argument once we have that horizontal geodesics do not branch, right? I'm not gonna prove the other items, so I apologize for that. Okay, so now I want to bring the curvature into play, right? I'm gonna recall a little bit about what RCD spaces are, but just to say what the moral notion of this is, it's a metric measure space, right? Such that it has a notion of bounded Ricci curvature from below and dimension bounded from above, right? I'm gonna give a definition which is not like the starting definition or like the first definition that had that occurred for RCD spaces, but I feel that it's the easiest one to explain, right? So let me recall this so-called Buckner inequality for manifolds, right? Which is this very well-known inequality that happens in manifolds, right? And that happens where this k is a real number, right? And this n is the dimension of my manifold, right? There's actually a surprising but easy to prove theorem which says that on a Riemannian manifold, it's equivalent to say that you have Ricci curvature bounded below by k than to say that the Buckner's inequality holds for all smooth functions, right? These two things are equivalent. So like morally, if I wanted to talk about Ricci curvature in metric measure spaces, we have like two options, right? Either you make sense of the Ricci tensor, right, and try to talk about this, or you try to talk about the Buckner's inequality, which turns out to be much more easier, right? Okay, so let me try to convince you in a couple of slides that it's possible to recover this notion of Buckner inequality for metric measure spaces, right? So basically, what I'm gonna try to say is that you can make sense of all the objects that appear in the Buckner's inequality. So it would be enough to talk about a norm of gradients of functions, right? And Laplacians of functions, and this sort of Riemannian metric in some sense of gradients on functions, right? So first, let me try to make sense of the norm of the gradient of a function. And for this, like the key point is to remember a variational characterization of this object in Rn. So for a C1 function in Rn and some G non-negative function continuous, it's the same to say that G majorizes the norm of the gradient of f than to say that this inequality holds, which is sort of like the fundamental theorem of calculus, right? And so, of course, the moral being that if you want to speak about this subject, you can try to say, okay, so consider all of the G's that do this, right? And take the minimum of these G's, right? This is sort of like the characterization, right? Now, of course, one thing that could be a little bit uncomfortable for metric measure spaces is this term here, right? So I have to restrict to the so-called class of absolutely continuous curves, which are curves for which this term exists, right? To be much more precise, a curve is absolutely continuous if there is some integrable function f such that this inequality holds, right? And if you have an absolutely continuous curve, then it turns out that this differential quotient exists, right? This so-called metric speed exists, right? And it plays the role of the f here, right? So if we restrict to absolutely continuous curves, then we can make sense of this inequality, right? And this is what Heinonen and Koskela did originally, right? So they defined that a Borel function G, non-negative Borel function G, is an upper gradient of a function f if for all absolutely continuous curves, the inequality holds, right? But it turns out that this is quite a restrictive notion because it could happen that you cannot take a minimal upper gradient of these G's. So you cannot really recover in all cases like the notion of norm of the gradient of f with this context. And so what Jiggly did is to sort of weaken this definition, right? Say we admit, we reinforce the regularity of G, say that we make it L2, right? And we're gonna say that this G is a weak upper gradient if the same inequality holds, but only for almost all curves, right? And to be much more precise, what this means is that we have an integrated version of this inequality against so-called test plans, which are a class of probability measures on the set of curves, right? This notion of test plan is a little bit technical. I'm not gonna say the definition of this, but maybe it just suffices to say that they are measures which do not concentrate too much mass. So they are like suitable to test this inequality, right? And so with this, you can always take a minimal weak upper gradient, right? And so if I look at the set of functions which have at least one weak upper gradient, and say you intersect with L2, you can get a notion of a Sobolev space in the usual way, right? If you let the minimal weak upper gradient, we denote it like the norm of the gradient of f. We even have like the usual Sobolev 1-2 norm, right? So now this covers the part about talking about the norm of the gradient of a function, right? As soon as I can take weak upper gradients, I can recover the notion of a norm of the gradient of a function. Now, if you think only like algebraically, then you can polarize this object, right? You can take the polarization of this norm of the gradient and define this sort of inner product in this way, right? Which will only be L1, right? And there's no reason to expect that this is bilinear, for example, right? So we have to impose it, right? If we want to have that this object is bilinear, we have to impose it, right? Okay, so that's that. And then finally, how to talk about Laplacians. Then we can take a note from the course of partial differential equations and just define it distributionally, right? If we have a notion of norm of the gradient, then I can get a notion of Laplacian by forcing the integration by parts formula, right? Okay, so a little bit fast, right? I guess, but then maybe you can see that you can make sense of all of the objects that appear on the Buckner's inequality, right? Of course, I'm being a little bit sloppy because we actually need an integrated version of this inequality, right? A weak version of this inequality because all of the objects that I spoke about are defined almost everywhere. So I have to be careful about this, right? But if you have like an integrated version of this inequality, this is equivalent to the usual Buckner's inequality, right? Okay, so with this we can define RCD spaces. Actually, I'm gonna go ahead and put the full definition here. This definition was given by Ambrosio, Gigli, and Savare in 2012, right? And it says the following. So a metric measure space is a Riemannian, it has the Riemannian curvature dimension condition for parameters k and n with these conditions, right? If the following holds, right? So the measure gives finite mass to bounded sets, which is something that I even required from the beginning. I'm not gonna worry too much about this thing, right? Secondly, the Sobolev space, the Sobolev 1-2 space is a Hilbert space, like I said before, right? And Buckner's inequality holds. This is morally the definition of RCD spaces, right? And there's a last condition that one requires. It's a technical condition, which as I put here, I'm gonna just forget about it for the rest of the talk. It's quite technical, but what it means, what it gets us is that we have no pathological spaces, say, where, for example, the only Sobolev functions are constant functions, or that, or say every function is a Sobolev function, for example. We can remove these pathological examples, right? This is in some sense what links like the geometry of the space, like the actual distance geometry of the space, to this functional analysis thing we define, right? But like if you want to think about this, like morally, an RCD space is just a space on which like the Buckner's inequality holds, right? And I want to think about this just as having Ricci curvature bounded from below. Okay, so just to mention a couple of examples, right, of RCD spaces, let me just put everything here, right? So, of course, manifolds with Ricci curvature bounded from below, these are examples of RCD spaces, right? Also, the so-called Ricci limit spaces, which are Gromov-Hausdorff limits or measured Gromov-Hausdorff limits of manifolds which have an upper bound on the dimension, right? A uniform upper bound on the dimension, a uniform lower bound on the Ricci curvature, and a uniform upper bound on the diameter. These were like extensively studied by Chigger and Kolding in the 90s. Also, Alexandrov spaces are examples of these RCD spaces, right? This was proved by Petrunin and Zhang and Zhu. We can do the usual constructions that you do on Alexandrov spaces. You can take cones and you can take suspensions, right? Of RCD spaces. I'm being a little bit sloppy here because I have to mention like the metric and the measure that you put on these spaces, but let me be a little bit sloppy here. And like the most important example for this talk is that because of work of Fernando and Martin Kell and Mondino and Sosa, you can also take quotients of RCD spaces by compactly group actions, right? Meaning that if you take an RCD space and you have a Lie group acting by isometries, which also preserve the reference measure, this is what I mean by isomorphisms, then the quotient space is also an RCD space with the same curvature bound, right? Okay, So just maybe 2 lines about what the structure of these, like the general structure of these spaces are, right? So one bad news about these spacers, as opposed to Alexandrov spaces, is that you can also take tangent cones, right? You can take a point on your space, and then you can blow up your space, right? Rescaling appropriately the distance and rescaling appropriately the measure, right? And then you can blow it up, and then you get a tangent cone at each point, right? But in Alexandrov spaces, this is always uniquely defined up to isometry, right? There's a unique tangent cone on each point. And this is no longer the case on RCD spaces. There may be several different tangent cones on each point. And the relevant theorem here of Mondino and Neighbor is that for almost every point, the set of tangent cones is uniquely defined, right? And it consists of a Euclidean space where the dimension of this Euclidean space is dependent on the point, right? I also consider this with the Euclidean distance and the Lebesgue measure, right? So potentially from point to point, we could have different Euclidean points, Euclidean spaces, right? But the key point here is that only one of these strata of points, right, has positive measure. So this gives me an idea of an essential dimension of my space, right? Like the K here that has this condition. And so this is more or less okay, right? And the other relevant theorem here is that you could wonder if, okay, could it happen that like the dimension, the essential dimension, could change from point to point? And the answer is that that no. And this answer was given by Brue and Semola for RCD spaces, right? And so they are similar to Alexandrov spaces, but not quite, right? And just to mention that some of the key tools for group actions in RCD spaces are already known. The Myers-Steenrod theorem was proved by Luis Guijarro and Jaime Santos, and also by Gerardo Sosa independently for RCD spaces. This is already known. And also the principal orbit theorem was proved in the work that I already quoted by Fernando, right? So these two notions are already known for RCD spaces, right? Okay, and so the other key theorem that we proved is that what structure you can give to the slice, right? So I'm gonna focus on on a subclass of RCD spaces, the so-called non-collapsed RCD spaces. So these are RCD spaces, right? But where the reference measure is not any reference measure, is in fact the Hausdorff measure, right? Where the n is this n, right? So this terminology of non-collapsed spaces, it comes from the fact that usually the dimension is less than this n, right? But when we equip it with the Hausdorff measure, then we have the same n, right? And so if I have a Lie group acting on a non-collapsed RCD space, right, such that the quotient space is of dimension 1, so say it's of cohomogeneity 1, then two things happen. So firstly, every slice, you can equip it with an RCD structure. And this is a non-negatively curved RCD structure, right? With some dimension bound. So the dimension bound here is that n minus k, where n is this n, right? And k is the dimension of the orbits of x0, right? And secondly, you can identify this slice with a metric cone, so like a true cone with a cone metric, right? Where the base of this cone is a homogeneous space, where now this homogeneous space has Ricci curvature greater than or equal to this number, right? In the Alexandrov case, you have like a homogeneous space with sectional curvature bound by this number, right? So I don't think I have too much time to say a little bit about the proof of this. Do I have like 5 minutes to say a little bit about the proof of this theorem?
maybe yeah, maybe 2 minutes or something like that. Yeah.
Yeah, okay, yeah. Actually, I'm gonna give a very
Okay, yeah.
yeah, okay. I'm gonna give a like a very rough sketch actually because the proof is quite involved. But at least the main idea is somewhat nice. So please take this with like a grain of salt. It's a very rough sketch, right? Okay, so take a sequence of numbers that goes to 0 and take the corresponding blow up of your space at some point x0, right? So take like a tangent cone that corresponds to this sequence of numbers, right? And now what you have on each of these rescalings of your space is that G acts by isometries on this rescaling, right? And you can use results of Fukaya and Yamaguchi to say that actually there's a limit group acting on the tangent cone by isometries, and it's actually acting effectively as soon as G acts effectively, right? So we have this limit group acting on the tangent cone. And now what I want to do now is try to produce lines on this space, on this tangent cone, right? I want to see that actually it has to contain a line. So what I'm gonna do now is that I'm gonna look at the isotropy of x0, right? And then I'm gonna look at the Lie algebra of G, and I'm gonna take a splitting of the Lie algebra, right? A splitting like this of the Lie algebra, where say this factor T is the Lie algebra of the isotropy of x0. So now for each vector on L, right, which is not 0, we can pick a sequence of numbers such that when we take these isometries, right, the ones that are produced by this sequence of numbers, when I apply them to x0, they converge in the blow up to some point in the tangent cone, right? But I want this point to be different from the base point of the tangent cone, right? So this gives us an isometry, right? Like the limit of these isometries. Say that we call this isometry phi b, right? And this isometry moves the base point of the tangent cone to some other point, right? But now, one very deep result from De Filippis and Gigli on non-collapsed spaces is that actually tangent cones on non-collapsed spaces are always metric cones, meaning that they are actually they have a cone metric, right? And so what I can do, if these are indeed cones, right, is to take a ray that comes from the base point of my tangent cone, right, and that passes through phi b of 0y, right? So I join this point to the base point of y, right? But now I have basically one, right? Because if I have this ray that goes from the base point and that passes through this point, I apply the inverse of this isometry, and now I get a line in my tangent cone, right? And I can do this for all of the b's, right? If I take different b's here, say linearly independent b's, then I get different lines here in the tangent cone, right? So this what this allows me to do is that I can apply Jiggly's splitting theorem, right? So because I'm blowing up my space, my tangent cone, it has the structure of an RCD 0n space. It's a non-negatively curved RCD space which contains lines, right? So I can split all of these lines and get another factor which has no lines, right? So after I split all of the possible lines, right? Say I split the maximum Euclidean space that I have, then the other factor is also an RCD space, right? It's an RCD 0, say K space, right? Which is also a metric cone and does not contain lines, right? But then this is where I'm like sweeping under the rug like a lot of details, right? You can see that actually this remaining part of the tangent cone is the part where the isotropy acts, right? It's not moving anything there. So you can identify this remaining part with the cone over the slice, right? Okay, so this is more or less like the proof, right? Because once you have this cone over the slice, and you know the cone is an RCD space, then the base also has to be an RCD space, right? And just to finish, maybe we applied this result to give a classification of low-dimensional non-collapsed RCD spaces, right? So what we proved with Diego and Jaime is that if G acts effectively by isometries which preserve the reference measure on a non-collapsed space, and this space has essential dimension less than or equal to 4, then actually this space has to be homeomorphic, actually equivariantly homeomorphic to an Alexandrov space. And so the classifications that we already had do hold, right? And like the proof is just like it's very silly actually, because like for dimension 1 and 2, this is due to very general and deep theorems of Kitabepu and Laxian and Lichok-Stadler, right? So Kitabepu and Laxian, they classified all one-dimensional RCD, non-collapsed RCD spaces. And Lichok-Stadler, they proved that two-dimensional RCD spaces are actually Alexandrov spaces, right? So we only have to worry about three-dimensional and four-dimensional spaces, say, right? But for this, you can proceed like in the usual manifold case, right? Because of the low dimension, you can bound the dimension of your group, right? Like this, right? You can bound the dimension of your group like this, right? And then if you are on low dimension, then this severely limits the possible groups that appear here, right? And so the classification of compactly groups in low dimension tells us what the possible groups are, the ones that are acting, right? But also when you look at the possible slices, right? Then you want to look at homogeneous spaces which have Ricci curvature bounded from below. But these are also low dimensional homogeneous spaces. And it turns out that in dimensions 3 and 4 and below, it's the same to have, or if you admit a metric of Ricci curvature bounded below, then you also admit a metric of sectional curvature bounded below. And so you fall back into the case of Alexandrov spaces that was already considered by many people. I'm gonna just mention a few here. So Fernando and Catherine, they classify the Alexandrov spaces, cohomogeneity 1 Alexandrov spaces in dimensions up to 4. Then Helcher and Parker also had some input in these dimensions. And in the manifold case, there was already work by Neumann, Mostert, and several other people that I'm forgetting here, right? And okay, so this is basically what I wanted to say. So thanks.
Well, thank you very much for a nice talk. Are there, maybe we have a couple of minutes for questions? Are there any questions?
So, hi, Mohammed. So, if you restrict attention to Ricci limit spaces, can one say more concerning the Slice Theorem? That's a great question. To be honest, I'm not sure because you could have a non-collapsed. So you could have non-collapsed RCD spaces that appear as limits, as Ricci limit spaces. So I'm not too sure. I guess I would have to think about this. Yeah, sorry for the bad answer. I'm not sure.
Okay, thanks for the question and for the answer. So, are there other questions? So, okay. Well, if not, maybe let's thank Jesús also again. Thank you everyone for joining,
Thanks.
and I hope to see you in the next session of the seminar. So, thanks.
All right, thanks. Cheers.
Yeah.